Okay, this lesson here is all about the idea of continuity, mathematical continuity, or just the idea of continuous functions. And one of the best ways to understand what a continuous function is to first understand what it is not. So we're going to look at some examples of what would make a discontinuous function. So I'm going to do this mostly through pictures, just to illustrate this. So we'll look at a couple of diagrams here. So I'll draw a picture like this, right? So most people would look at something like this and say that, this is an example of a function that is not continuous. And the main reason for that is it is not continuous at the point x equals a. So the problem here is that the function has a break at this point. So f of a is something that you can't calculate. So we could just say this, right? F of a doesn't exist. Okay, so what we're going to do is we're going to look at more pictures where the functions are still discontinuous, but we're going to fix the first condition here. So in order to do this, I'll draw a picture here where this is covered, right? Where f of a does exist. So I'll put a dot right here, and then that will take care of that. And so I'll draw the function like this. So this is a new function. So still here, this is a discontinuous function, but you can't use this reason, right? You can't say f of a doesn't exist. You could definitely see the output there. But most people would still say this function is a discontinuous function. And the main reason for that is the limit doesn't exist as x approaches a. So you'll notice as we approach a from the right-hand side, we're following this branch of the function, and the limit would be here. As we approach a from the left, we would be following a different branch, and the limit would be here. So for that reason, this function is also a discontinuous function at x equals a. So we could say here, the limit of the function as x approaches a, this doesn't exist. So this is yet another reason that a function could be discontinuous. So the last thing we're going to do is now look at an example where we can't use either of these reasons, but we would still say that the function is discontinuous. So this we could call, I guess, the third situation. Alright, so I'm going to cover both conditions here. So we're going to fill in a dot, right? So the function is going to be defined there, and we're also going to make sure that the limit exists. Okay. So still, if you look at this function, people would say this is a discontinuous function, but you can't use reason number one. You can't say f of a doesn't exist, because it does. And you can't use reason number two by saying that the limit doesn't exist, because the function will get closer and closer to this location here. So naturally, the problem with this one, the reason it's still discontinuous, is those two conditions don't agree. So we can write this here, the limit of the function as x tends to a, this is not the same as f of a. So even though we do have the output at a, and we do have a limit that exists, the problem here is they are not the same. So this is still a picture of a discontinuous function. So if you take a minute to think about the three examples that we just saw, all of these examples show you discontinuous functions. So this is exactly how you can pretty much develop the definition of continuity, is by taking the negation, right, or the opposite of those three conditions. So I'm going to put this definition right here so you guys can see it, right? So if you look in your textbook, this is the typical definition for what it means for a function to be continuous at a point. Right? So here we're talking about just local continuity. So for f to be continuous at a point, right, we need three conditions to hold. And the first one here is that f of a needs to be defined, and we saw that in the first diagram. The second condition is the limit must exist. Okay? And then without a doubt, the third condition is the most important. You can see the opposite of it right here, and that is these two conditions must be related in terms of equality. So the limit of the function as x approaches a is equal to the function value at that point. And the natural consequence of this is when you're taking limits of continuous functions at a point, that means the way you can do it is to simply directly substitute, right? So you can just plug the number in. So this is the natural definition for continuity, and it's best to look at this through examples of discontinuous functions. Okay, so I'm going to look at a quick example now, just to discuss the continuity of a function. And we'll just keep it pretty simple. We've seen enough examples like this in class. So here's an example of a function. You could tell right away at -2 this function is going to have a problem. So we could just make a note here. X can't be -2 because if it is, we're dividing by 0. So what we're going to do in this example is just talk about where this function is discontinuous and where it's continuous. So we can do a little bit of the algebra here, and you guys have seen this in previous videos. So you do the simple algebra, and so you can remove this factor here, right, that is affected by this, and then this new function becomes x minus 2. And so this is only valid provided we stay away from -2. So we should add that disclaimer. So x cannot be -2. So otherwise, this function here is going to look like a straight line, like y equals x minus 2. So here we still have a discontinuity, right, at x equals -2. And so to look at the graph, right, so this here is going to have a discontinuity at -2. So it's going to have a hole there, but otherwise it's going to look very much like a straight line. So we're going to drop down here. And so this will be at -2, -4. So we'll have a hole in the graph right here, but otherwise it's going to look like y equals x minus 2. And continue onward in this way here. So this function definitely has a discontinuity at this point, right, when x is equal to -2. In fact, it has a hole at -2, -4, but it does have a limit there. So we could say that the function is perfectly continuous as long as we stay away from this point, right? Stay away from -2. So the way we usually write this, right, in interval notation, you could say the function is continuous to the left of -2. So we write that as -infinity to -2. And it's also continuous to the right of -2. So you combine that with -2, positive infinity. So we create these two intervals to the left of -2 and combine that with to the right of -2. So you could either say it's continuous here, or it's simply discontinuous when x equals -2. Okay, so the last couple of things to talk about, because the beginning of this lesson is all about continuity at a point. So we're going to generalize that just a little bit to these basic ideas, right? And these are pretty common extensions. So you can talk about what it means for a function to be continuous on an interval. And so this means you're continuous at every single point inside of a window. And then we typically in algebra talk about continuity on open intervals. So what we can talk about in calculus is this endpoint continuity. So it turns out sometimes your function is continuous on an interval, but it's also continuous at the endpoints, right? Because there's no problem with the endpoint behavior. So we'll just keep these ideas in mind as we look at some different examples. Right? So I'm going to go through 3 really quick ones here. So I'm going to put this information up here. So the examples I'm going to show you are pretty typical mathematical functions, and I'm going to show you a window on the right-hand side where we can say that this function is continuous on this interval. And notice this is an open interval, -π/2 to π/2. And the reason it's open has a lot to do with the tangent function. So if we graph this here, I'll put in the asymptotes. So we have one at -π/2, and then one at π/2. And then you think about just the tangent graph, what it looks like. So this is not going to be perfect, but close enough, right? The tangent graph has asymptotes at negative 90 degrees and positive 90 degrees, and this is the reason for saying that the function is perfectly continuous on this window, but you can't include the endpoints because of the asymptotic behavior, right? And then the tangent continues on, right? It's a periodic function, but we definitely cannot include these endpoints because of this strange kind of behavior. So we would say this function is continuous here, but we'd have to leave it at that, right? Open interval negative pi over 2 to pi over 2. Okay, so now we're going to move to a much more common example. This is one that we should be pretty familiar with, the squaring function. So here we go. I'll go through this one pretty quickly. So again, we're going to look at a graph, right? Y equals x squared. So I could probably get rid of this space here, right? I don't really need it. Okay, so again, it's perfectly fine to say this function is continuous, right, on the window 1 to 3. So if we look, for example, from 1 all the way to 3, there are no gaps or jumps or strange things occurring, right, on this window, on this little interval or this window here. But what you'll notice here is that this function is actually continuous beyond 1 and 3. So talking about endpoint continuity is relevant in this case, right? Because you could pick up the endpoints and we would still know a way of interpreting the interval 1 to 3 if it were closed. So two things that we write here, you could say the limit of this function of g of x. And so as x approaches 1 from the positive side, this is equal to g of 1. So the key here is we're looking inside this window from 1 to 3, but if you approach one of the endpoints from the inside of the window, so if you approach 1 from the positive side, notice that the limit is equal to the function value g of 1. So this means that we could include the left endpoint for continuity. And a very similar idea, you could go the other way. You could approach 3 from the left-hand side. So I'll write down that statement as well. So the limit of g of x as x approaches 3 from the left, this is equal to the output at that point. It's equal to g of 3. So what we could really do is say, sure, this function is continuous on the window, the open interval 1 to 3, but because of this endpoint continuity, we can update this interval, right? And we could say it's continuous on the closed window 1 to 3. So that's really all that is meant by endpoint continuity, or being continuous on a closed interval. Okay, I'll do one last one with you here, and then we'll talk about the theorem. Okay, so we'll talk about another pretty common function in algebra, and this is the square root function. Okay, and you guys might recognize the shape of the function. Okay, we can only take the square root of positive values, right, if we're going to stay with the real numbers here. So this is the graph, and if you think about this for a minute, I think you can predict what's going to happen. Again, this window, you could say this function is continuous on this interval without a problem, but notice that you can approach one of the points from the right-hand side, and the limit of the function as we approach 0 from the right is equal to the function value at 0. So we could say the limit of this function as x is tending to 0 from the right is equal to the output at 0, right? This location right here. So we can update this window and say it is continuous on the interval 0 to infinity, but we can include the left endpoint. We're going to make that closed there. And infinity, generally speaking, this is an abstract entity, so we leave off that point. But the point here is you can have continuity on closed intervals. They could be half open, half closed, or they could be fully closed. Alright, so very last idea here. This is a really important mathematical theorem. It's used a lot in calculus, really, to prove other theorems. And so here's the name. This is called the intermediate value theorem. So I'm going to show you a statement of the theorem, and then we'll just look at a picture to make sure we understand what the theorem is really saying. Okay. So the intermediate value theorem says we have a function that's continuous on a closed window. And that's that thing that we just talked about, right? So it's continuous on the open interval a to b, but it includes the endpoints. And then it says that k is any number between f of a and f of b. So the big thing about this theorem is these are all the assumptions that we're talking about. So these are things that we assume. As soon as you see the word then here comes the conclusion. So it says, then there exists a number c, and this number must fall somewhere in that window. So the number c is in AB, such that if you calculate the function value at c, it's going to map to that previous value that we call k. So I'm going to leave the theorem up here and just draw a diagram so we can see what's happening. So I'll put the diagram right here. Okay, so the function f is continuous from a to b, so I'm going to keep this nice and simple. There's no point in making it complicated. So I'm going to put f of a here and maybe f of b here. And so we have continuity on a closed window. So this is our function f, and we're including these 2 points here. So we can label this here. We can see f of a is here, and f of b is up here. So the function is continuous there. And so then it says k is any number between f of a and f of b. So what you can do is just select a number that's in between, right? So k falls in between these two extremes, f of a and f of b. And then the conclusion of the theorem says there's another number that corresponds with k, and that number c falls in the interval ab. So here f of c equals k. And the way you can find that is you can go back and follow your function and find it, and then drop straight down, and you can find your c value. So you can see right here, this point here corresponds, f of c is equal to k. So really what the theorem is saying, right, is you can take any number between the extremities, f of a and f of b, and you're going to be able to find a number somewhere on the x-axis in between a and b, so that if you calculate the value at this point, it's going to map directly to that. And informally, what this says mathematically is anytime you have a continuous function on a closed interval, right, that function is going to assume every value between the extremities. So in this case, f of a is the low point and f of b is the high point, but k here is a point that's just arbitrary in between, so the function values have to really climb in between every single number, right, between f of a and f of b.